Yeah. No, thanks, Mike, Ian, for organizing this. It's very nice to see a lot of familiar faces here. I'm a little bit sorry for Jake that I just saw online because he saw this presentation or a very similar one like a couple of weeks ago at the UK CIS meeting. So sorry about that if you got up just for this. But yeah, just to stay in theme with like the previous South African presentation, this work also involves some people from South Africa, in particular Marcello and Francesca. So an Italian team all scattered around the world. And it's a toy project, I'd say, that we started under the impetus of Marcello and mine, and we pushed Francesca, which was the main driver of this work, in which we decided to use wave attenuation in particular to estimate Antarctic sea ice thickness. And most of the work that I'm going to present today has been published in this ocean modeling paper very recently. So as Rutger presented before, Antarctic sea ice extent is highly variable in season. We have a minimum after the summer of about 2 million square kilometers, give it or take, and a high in September, October of about 18, 20 million square kilometers. And we all know that in 2023 was a record minimum for sea ice extent. Now, and this is well known that the air is variable, but what about thickness? We have far less information about the thickness and so the volume of the Antarctic sea ice cover. And one of the problems that we have with Antarctic sea ice thickness is that in situ measurements are low in coverage in both time and space. It's quite challenging to do there and do measurement, spatially distributed measurement, especially in some challenging season like the winter, and like the South Africans have shown us that it's quite hard to get to ship time and go down there to do those measurements. And so what a lot of people do is to rely on remote sensing. However, albeit this is as a wider spatial and temporal resolution, it's quite uncertain, mainly due to the snow cover and the limited validation. So we go back to the fact that we don't have in situ measurement to validate the remote sensing product. And as a result, the error can reach up to 50%. And that's in a slightly old paper in terms of sea ice. It's 5 years old paper, and stuff are moving fast in that realm. However, very recently, this paper came out, this product came out, which is the sea ice thickness from SMOS version 3.3. And it's a paper 2024 from Kalesh. And it gives the sea ice thickness up to 1 meter at a daily resolution of 12.5 kilometers, plus an uncertain map. There are a few hypotheses under this product. The main one is that the sea ice cover is 100%, so close sea ice cover. And second, it's an experimental product. Experimental means that so far it has been adapted from the Arctic, okay? Now, this is a working group about marginalized zone, and I shouldn't explain what's the marginalized zone, but broadly speaking, is the area where wave and sea ice properties affect each other. We also see that there is some thermodynamics, as I was going to explain, but I'm mostly focused on the dynamics of this area. Okay, and so the idea is that if we have waves in sea ice and we measure them during the scale cruise, for example, in 2017, in which we measure significant wave height about 5 meters at 50 kilometers from the sea ice edge in what was a sea ice concentration of 8%. So there are waves in the sea ice, even in 100% sea ice concentration. And we show that also with remote sensing. Alex, I think, is in the audience, Alex Fraser, and one of his students did this work in which it demonstrated that waves can propagate up to 180 kilometers into the marginalized zone. So the marginalized zone is far deeper than the 80% threshold would say us. And again, Noah, I think, is as well in the audience. He ran some models of waves and sea ice coupling size model. And it showed that the extent of the marginalized zone defined more by its properties rather than the concentration agrees with what we measure with remote sensing product. And so this is a wide area that extends up to 250, 300 kilometers. And the question that we had was like, can we use wave properties to infer sea ice thickness? Because wave properties and sea ice thickness are related to each other. To do that, we need to have a model for how waves attenuate into the sea ice. And here where Francesca comes into place, Francesca De Santi, because we decided to use a model, the calibrated close packing model, which is a generalized viscous layer model. Vernon Square, in his review in 2020, wrote nice words about this model, so we embraced it. The models are embedded in Gray's ice, very similar to what Rutger does. And so all the forces between the flows are due to contact forces, which are inelastic collision. The model, similar to any other model, gives an exponential attenuation. So it gives an exponential attenuation. The advantage of this model is that this attenuation is function of both the frequency to a power 5 that has been observed around. Jim Thompson has observed it in the Antarctic marginal zone, but also importantly for our purpose of the sea ice thickness to the power 1.5, 3.5. Now, as every model, there is a coefficient in front of the attenuation rate, that -10 in this case. The good thing is that the -10 was calibrated for the Alden-Stone beta, okay? And so we decided to adopt that, okay? That was from a paper of the Carlos in 2021, scientific report. And it has been seen that this inclusion of the thickness dependence on the wave attenuation increases agreement with measurements, not only in the Alden-Stone, so in Greenland, but also with measurements that we have in the Western Arctic in 2015, so in the Arctic, and the Weather Sea, so in Antarctica in 2000. And so the largest available database is surely to verify our hypothesis is the paper 2017 that probably doesn't need any introduction. And this data set is freely available, Kohout 2020, ANAS Glaciology, and more importantly, Rogers 2021 in Core Regional Science Technology also provided attenuation profile. That's the key point of our work for all the buoys and all the points. So all the attenuation profile, Ka as a function of the frequency, are obtained from measurements using the spectral wave model, WaveWatch3, which is a state-of-the-art wave model. Okay. In the top, you see the concentration as detected from the MSR2, the position of the buoys, I don't remember exactly which day, and the main direction of the waves. Okay. And now, on those measurements, on those attenuation profile, we can apply the CP model, use an inversion, and fundamentally retrieve the ice thickness as an average measure over the frequencies and the distance traveled by the waves across sea ice. Now, what we do, we compare with the SMOS version 3.3, so remote sensing, against the inversion from the ice thickness. In total, we have 2006 data. The data are quite scattered. But the correlation coefficient is not bad at all. It's about 55%. Okay. Now, those are color-coded by the sea ice concentration retrieved from remote sensing, so MSR2. And if you remember at the very beginning, I said that the product, the SMOS version 3.3, is given with an uncertainty, because the uncertainty is given by the concentration. It's a reminder that both the model, the SMOS, is calibrated for full 100% ice cover, and also the closed pack model is more suitable for closed pack conditions, so high ice concentration. And if you decide to only look at those data, those for CI's concentration higher than 90%. Unfortunately, we have a lower number of matches, only 271 data, but the correlation coefficient increased to 86%. And here I decided to plot only those with CI's concentration higher than 90%. So you can more clearly see that there is a broad agreement between the remote sensing product, which is experimental, and our retrieved ice thickness, which is quite promising. So it basically, we achieve what we want to do. We derive some ice thickness based on the wave attenuation. Now, waves are multimodal, so our thickness is a function of the frequency because our attenuation rate is a function of the frequency. And so one of the ideas that we had was like, okay, besides only looking at separating the data according to CI's concentration, let's also look at what happens at each individual frequency. And here in the plot on the left, you see the correlation coefficient as a function of the wave frequency. The highest correlation, as before, is for the high CI's concentration, higher than 90%, in the dark blue curve. And interestingly, it has a peak of very high correlation, superior to 0.8, for a wave frequency around 0.09 Hz. That's quite interesting. It's quite useful because those frequencies are about 11 seconds or 192 meters, which are the typical wavelength that we find in swell waves in the Southern Ocean. There are a lot of swells. It's fundamentally an unlimited fetch. And so those are very long waves where most of the energy, wave energy of the Southern Ocean exists. So we have higher correlation for where there is a lot of signal. So the signal to noise ratio is very high. And this is quite encouraging because it allows us to only look at swell wave attenuation, which survives the longest. If you go back to the work of Brouwer and Sir Alex Fraser, we saw that those waves are the ones that survive the longest. And so it's quite useful to have those waves associated to the swell that survive longer, to have more signal that allow us to retrieve the sea ice thickness. I think I went a little bit too fast in this presentation. I should have added a few more slides. But nevertheless, I'll jump into the conclusion. And so it's a very small paper, but the key concept that I want to summarize was that indeed we can use waves to estimate Antarctic sea ice thickness. And we can do that using physically based calibrated closed path model for wave attenuation in our case, which proved to be quite good. Moreover, the sea ice thickness from wave attenuation has good correlation with remote sensing products that have been recently released, in particular for the sea ice concentration. And it's important to note that both the SMOS product and the CP model are calibrated for those conditions. And it's quite encouraging that the agreement is passed for swell waves, which are typical in the Southern Ocean. And it's quite promising for the future of using this kind of technique to infer sea ice thickness in the Antarctic sea ice in the future. So with this, I want to conclude. I went very, very fast, and so there is quite a lot of time for questions. Thank you very much for the attention.
Okay, Alberto, it's a really interesting result. Yeah, do we have questions? Yeah, Alex.
Thanks, Ian. Thanks, Alberto. Very nice to see your lovely face from this side of the world. In the Kaleshka paper, they made a point of saying that it's really hard to validate their product. I know that because I was the editor of that paper. And I know that Lars would be super interested to see this very high correlation between that you showed here, the 86%. So yeah, if you haven't already, definitely get in contact with him because I think it's great.
He saw our paper because when we submitted the paper, it was still under review. And then he sent us an email, the paper has been accepted, here it is. So we've been in contact with him.
Very nice. He would
I think he was pleased to see that
Yeah.
there was quite a good agreement.
Yeah, it's great work. Thanks for sharing.
And yeah, I think Alex, you've done some work looking and with Gilles. I remember that in the paper in the cryosphere, you look frequency to frequency, and I think that's quite useful in that sense because you only have to look at those frequency, those long wave components, which are associated to most of the energy to then retrieve the thickness.
Yeah.
So there is a lot of work that can be done in this realm.
Yeah, and Joey Vormans is working on using Jill's data set to look at the attenuation rates. And he also
So
used
his
the SMOS
presentation
product as well.
recently,
Yeah. And that's up on discussions now on EGU Sphere or whatever it's called. So check that out.
Okay. Oh yeah. No, I know the presentation because when it came to Europe to EGU and
Yeah.
CWF, he presented that work.
Yeah, great. Thanks again.
Alberto, can I ask a question? It's Luke, by the way.
Is it? Really?
Hi, how
Okay,
you
nice.
doing? Can you just clarify one thing for me? Maybe this wasn't concentrating hard enough at this point during your talk, but you're using the Rogers et al. Inversion method on the data, right?
Yes.
And that doesn't prescribe an attenuation model. It just looks for the best attenuation. Is about what I understand of it. Is it correct?
Correct. That's why we use it.
So
Because it doesn't assume any model.
when does the de Santi model come in?
On the inversion. What is it? I mean, like, it's basically this formula. The KIF is the one from Rogers.
Right. Okay. So there are like
and so it's on the
there are two
inversion
attenuation
rate.
rates in this process.
Yeah.
Okay.
I mean,
Right.
the direct form is the one here on the right. So the attenuation rate is -10 h to the 3 half frequency to the 5 distant.
Can I maybe like to interrupt, but
Yeah, sure.
I'm curious about that formula. I've never seen it before, but because it doesn't fit exactly what we've seen. Where did that come from? How validated is that? How valid is that? Because it seems like what you're doing is so in a sense, what you're doing is also correlating that model.
So, okay. It's like any other viscous model, right? With a frequency-dependent attenuation, right? There is mounting evidence that if you include a thickness dependence, you improve the results. And there is a paper by Rogers as well. I think it's a 2022 in which he did the reanalysis of all the data for the pipers, also including a thickness dependence. So instead of only using the frequency, also use the thickness to constrain the attenuation rate. Okay. Now, there is this paper in the past in which they did a little bit of data mining, let's say, and they came up with a dependence that I think it was frequency to the 4.5, right? And the thickness had a similar dependence because those two are correlated. So the exponent that you have on the thickness is correlated to the one on the frequency. Now, those values, the advantages that they come out from the model of Francesca, right? The model is quite complicated, and I admit I don't understand all the bits. That's only the final formula, okay? The good thing is that Thomson, with the data from the marginalized Antarctica, he found a 4.9 exponent. So it's quite close to that f to the 5, right? And also, like, the reality of the fact is that this attenuation rate frequency to the 5/5 in previous work, it was compared with those data in the Arctic, in Greenland, and in the Weddell Sea. So that's why we decided to use it. It's like any other model. It gave us a little bit more confidence in using this thickness dependency. I know that, Mike, you have the model in which you have the frequency to the third, right? In which you also put some thickness in there. You still have a coefficient in front, which it's not very well constrained. But the advantage of this model is that the coefficient is -10 for all the cases in which it has been calibrated, or about -10. So it's quite constrained. I don't know if it makes sense what I say.
Yeah, no, that's exactly right. So it's whether it's the third power or the fifth power is, you know, something that will be really interesting to understand. Like, and I just haven't seen that. I wasn't aware of all this work. So obviously there's a lot of evidence for that model. And this is more for thinner ice, but you've applied it across all these measurements, right?
Yeah, we applied to the pipers. It looked nice, and I mean, I think it was Werner in his review that say good things about the model, so that's why we decided to go with it.
So just to complete my thought, and I was being a bit slow there, but is it not possible to be consistent in using this attenuation throughout the algorithm that you developed?
Which algorithm?
To go from the data to the thickness prediction without using the inversion in there.
Yeah, we can. Yeah, the problem. Yeah, from the data instead of the Rogers, you mean?
Yeah, exactly. Yeah.
Fabian can tell you a word or two about those data. We decide to use the inversion because they were cleaner. It's
all right,
when you go on the data,
I'll
you
leave
don't even know
it there.
where the
We'll
waves
discuss
are
another
coming
time.
from.
Nice work.
Yeah, Alberto, that's Fabian here. Great talk, thanks. Just quick question. I mean, yeah, a comment, I guess. I think it would be nice to try maybe also other models, you know, to see whether you find. I mean, it's possible you may find very similar correlation. I mean, Mike and Luke had this model which has a, I think, linear thickness dependence in what's that 2017 paper.
Right.
I mean, I'll be interesting to see if that's, you know, worse, better, as good. I don't know. And then you have more complicated models, which, you know, are like viscoelastic type model, where of course you have more parameters in there you need to take into account, but and they don't have like neat thickness dependence, but they still have a thickness dependence. So
no, I do agree with you, Fabian, but I think the main point of this one is that the only parameter is that -10 on the front, and
right.
it seems to be fairly general. That's the real advantage of this one.
So what if you perturb this parameter? What happens? Have you tried that?
No, we haven't. Actually, we haven't, because that value seemed to work everywhere, and so we kept it. So it didn't need any specific tuning for this case. That I think it was the main point.
Okay, I should read the paper.
It's a short one.
Okay, that's better.
Like the talk, Alberto.
That's right.
Yeah, well, it's great. It's you know, it's great to see this, and it's, you know, to see what you're doing, Alberto, as well. Like, this looks really interesting. And I mean, it's the simple model here. If it works, would be brilliant.
Yeah, I mean, it's a simple model, but you should read the original paper. It's not that simple. I tried to get into it a few times, and it's
what is the original paper? Is this is the one by
the 2017 up there?
2017.
Yeah.
Okay, the Greenland 2017. I'm reading this one and the scientific report right now, trying to understand. It looks complicated as well.
Yeah,
all right.
No, it's a nightmare, the paper. She tried to understand it to me like 5 or 6 times and still struggling. I mean,
What's
I
the
think
paper?
it's cleaner on the Carol list, but it's just the usage of the model.
Okay. And why is it the Odin ice tongue data? Did they measure the ice tongue motion, Alberto? Probably some of the stuff.
I think they had some remote sensing. They did some remote sensing. They calibrated the attenuation rate because, like, the -10 is in principle similar to the viscosity that you put in there, which it's an equivalent viscosity. It's not the actual viscosity. And so that's a calibration parameter. But as I said, the main point is that we didn't have to change it.